Hi, welcome to my channel. Today we're gonna start talking about circuit analysis, which is typically a first course in electrical engineering, and it is usually taught in the first or second semester of the sophomore year of an electrical engineering curriculum. So the basic goal is to familiarize students with how to analyze linear circuits, which involve resistors, capacitors, inductors, and possibly they may include operational amplifiers. Now that depends on each university or college and how they prefer to space out their curriculum and courses. But in this lecture series, we're going to include what is listed here in the under goals, which I'm going to show you in a second. So we're going to be talking about voltages across and currents through linear circuits. And again, these linear circuits involve, we're going to be talking about what exactly constitutes a linear circuit. But for now, these involve circuits containing resistors, inductors, capacitors. And after that, we're going to be looking at some properties that follow or are a result of linear circuit theory. And we're going to see that they simplify our lives a lot and save us some computation time and setup time for setting up the circuit and writing algebraic equations for them. Then we're going to be looking at op-amp analysis. Op-amp stands for operational amplifier, and these are very common elements used in typically low frequency design. You don't typically use them for higher than a couple hundred or a couple megahertz and above. You don't really go, as far as I've seen, you don't go beyond that because something called the gain starts to drop, and there's a lot of parasitics at a certain point. And basically, if you go, for example, into RF and microwave design, you would not use op-amps for that. So for power circuits, for error amplifiers, for low dropout regulators, they could be used for basically anything in a couple, maybe a couple hundred kilohertz be a reasonable range, or anything below that. So basically, op-amps are very important for, let's say, DC or low frequency circuit analysis and design. And after that, we're going to be looking at first order and second order circuits. And the reason they're called first order and second order, it refers to the differential equations that describe them. So you have a first order equation or a second order differential equation, and this refers to the degree of the differential. So the first derivative, a differential equation with only one derivative in it would be a first order equation. A differential equation with two derivatives would be a second order differential equation. We're going to see where and why that comes about, and I may create some primer videos so that you don't have to go through a differential equation list and try to, or get lost in a long series of lectures not knowing what's more important and what's not as important for this lecture series. So I'll go through some examples and go through some primers so that we can focus our efforts in what is necessary for our lecture series. Then we're going to be looking at, these are not necessarily in order, some of these, so we're going to be looking at sinusoidal steady state and frequency response. So sinusoidal steady state is the idea that you want to look at phasors, which are certain quantities that simplify the math needed to analyze these circuits. And the steady state refers to, so we have something called transient and steady state analysis. For transients, that's, for example, when you have a, say, RLC circuit and you have a switch and you have a voltage source, and you turn the switch on and off and on and off in a certain manner. And the transient in this case refers to the voltage or current waveform, which can be abruptly changing because you have a, for example, if you have an inductor, we're going to see later on that if you have an inductor, if you, what it likes to do is that to maintain the current as steady as possible, and if you suddenly switch, turn the switch on or off, what's going to happen is that you're disrupting that current And so to be able to maintain a certain amount of current, the electromagnetic laws that govern the behavior of an inductor require to create a very sudden spike in voltage, something called kickback. It's going to create a spike in voltage and basically damage particular parts of your circuit. That's why, for example, we can design protection circuits to protect against such spikes, because for example, you don't want a user to have to worry about, okay, here's a black box, here's a switch, I don't want to have to worry about what's going to happen if I turn this on or off right now or in a certain manner. So these are certain things that we're going to be looking at, and certain design considerations. At some point we're going to be looking at applications, and we will see some of these pointers. So either way, that's transience, is the idea that how does your current or voltage change as you have sudden changes in the circuit, whether it's at the input or you're actually just switching it in a certain way. And then the steady state analysis is where we have something happens, you turn something on or off, or switch on or off, and basically you look at the output waveform, whether it's current or voltage, and steady state means that some time, certain amount of time has passed, whether that's a few time constants or a long time as t approaches infinity, if you want to speak mathematically. And that basically kind of simplifies analysis if you look at steady state, because you're looking at singular frequencies. So anyways, I won't spend too much time on that right now. Basically, I'm just trying to introduce you, give you a high-level view of what's going to be going on. And once we cover the fundamentals, the DC analysis, the AC analysis of these circuits, and RLC circuits, we're going to be looking at more advanced topics which require differential equations. So Laplace transforms, which is a way to analyze transient as well as steady state analysis. It basically encapsulates both initial conditions to a circuit and what's going to be happening later on. You're going to encompass all that into one operation, which is the Laplace transform, and the inverse Laplace transform, which we will see what the concept is and how it applies to circuits and why it's so useful. Then it is the Fourier transform, which is sort of a special case of the Laplace transform, sort of the steady state version of Laplace transform. You'll also see that as well. And then there's the two-port networks part, which is very important in the sense that if you have a certain system, composed of several circuits or one circuit, if you want to cascade them, you want to be able to quickly and efficiently come up with the relations of the input and the output, as well as the effects of the input to the output and the effects of output to the input. And there's certain network parameters, Z parameters, Y parameters, hybrid parameters, S parameters. We're not going to get into that's more of an RF microwave concept, and requires some understanding of reflections and some of the electromagnetics that I'm hoping to be able to do at some later point once I make good progress in this lecture series. We will get into that later, but for now we're going to kind of start from the ground up and do what's typically done at universities and start with a basic circuit course. So once you get these concepts down, you're pretty much good to go on them in the next level course, which could be BJT based amplifier design, bipolar junction transistors, MOSFETs, metal oxide, semiconductor field effect transistors. So, and those are again some of the video series that I'll be working on later on once I finish this one, or once I make significant progress in this one. And keep in mind, I do have a full-time job and other responsibilities, so I'm going to try to do this as much as I can, but one at a time is what I'm going to be focusing on. So now let's talk about prerequisites. So it's essential that you're very comfortable with algebra. You shouldn't have to think too much about it. You should be able to solve systems of linear equations pretty quickly, be able to manipulate equations quickly. Trigonometry is also very essential in electrical engineering overall. Whatever sub-discipline you work in, you're going to be seeing trigonometry and algebra, absolutely. Then there's calculus. You're going to need to know differential and integral calculus and the differentiation and integration of basic signals such as exponential, such as sinusoids, sines, cosines, and whatnot. Complex numbers are very important in the sense that once you work with that trigonometry, you don't want to be working with sines and cosines all the time when you have certain sources, or when you have inductors, capacitors, and they all have different voltages and currents where they have different phases. You don't want to be working with arguments in a sine function, for example, say, I don't know, say 2 pi t plus 30 degrees. It's just an example. You don't want to, when you're adding that or subtracting that or multiplying that with another sinusoid, you don't want to have to keep using trigonometric identities. So what you do is turn your quantities to real and imaginary parts, which are complex numbers. And what you do is you do the algebraic manipulations, the complex algebra, and what you do then is, once you finish the complex algebra, whatever the manipulations are, addition, subtraction, multiplication, conjugation, once you get done with that, you basically convert the quantity back into either sinusoid or polar form or exponential form, depending on what the problem asks you. And you should be comfortable going between said forms. And that's going to be of enormous help because it's efficient, it saves us time, and it's just a very useful concept to know. Then there's linear algebra, and the squiggly lines mean just, you don't have to know all of it, just be proficient in the basics of it. Linear algebra, you should be able to do matrix manipulations, be able to determine the dimension after like multiplication, for example, be able to multiply matrices, add matrices, subtract matrices, invert matrices, and some of the fundamental properties of linear algebra. Differential equations is also, it's sort of essential in the sense that as it applies to first order and second order circuits, you should be comfortable with knowing how to set up the circuits and how to come up with the solutions to the circuits, or be able to guess at least what form the solution will take. So these are the basics here, and before it becomes too long, I'll go ahead and end it here, and I'll see you in the next video. Thank you.